the physics video lecture, Physics 105B, video lecture 24. We're talking about the inertial tensor. And let's just review a bit. I think there was a mistake at the end of the last lecture that we'll clear up right here. So for the rigid body, instead of just having a moment of inertia, we actually have an inertial tensor. And that's a 3x3 matrix, so there's a little more going on. And but we already saw how completely logical it is. So here's what we have for the rotational kinetic energy. We have 1/2 double sum I and j, I sub I j, omega I, omega j, where omega is a vector. You know, I write columns and rows interchangeably. Right now I'm writing it as a column. So omega is this vector of the angular velocity. This is a quadratic form. And we had already seen that if you're just rotating around a principal axis, you just end up with 1/2 times one of these diagonal components times that component of the omega squared. Okay, so it was very, it was intuitive in that sense. Okay. It's intuitive, but there's simply more going on. So we've had the rotational kinetic energy, and we have the angular momentum, and now this matrix I, so I is a matrix, so we could go ahead and write this as in component form. This is a matrix multiplication, row times column. So we could say I sub k is equal to sum over I sub k n omega n, for instance, n equal 1 to 3. Okay. So that's the kth row times this column here. And so for that example I had given, I may not have gotten it quite right. Well, I'll return to that example from last time, because that was an important point about L and omega not being parallel. So let's go ahead and let our omega vector be omega 0, 0. So we're just rotating about the one axis. So, and you know, this is our rigid body. It's got its center of mass here, x1, x2, x3. Actually, for the purposes of this picture, let's mix it up a bit. Maybe we get it wrong both times. Okay. Suppose we're rotating about the x3 axis. We can simply visualize that better right here. Okay. Yeah, we're rotating around that axis. But this is that blob. It's not some symmetric shape, and we're at the, and there's the center of mass at the origin there. Okay, so what about L? We're going to write this out completely, which is what I could have done last time. So we're going to write the entire matrix out. I11, I12, 3. After all, this is just bookkeeping. 2, 2, 2, 3. I saw last time I had just started that and written a bunch of zeros. Let's go ahead and do it this way. Okay. So now we have omega 1, omega 2, omega 3, but we only have 0, 0 omega. Okay. So now what do we have? This is row times column. So the row times the column, we have I13 omega. Second row times the column, I23 omega. And the third row times the column, oops, that's a 3, 3. I33. That's omega. Okay. And so right there you see we're rotating about this axis here, as indicated with the little red arrow. But the angular momentum is not parallel, otherwise it would only have this component right here. So parallel would mean the inertial tensor only has this I sub 3, 3 here. In terms of 1, 3, 2, 3, 3, 3, okay, in terms of these guys right there. It says nothing about the diagonal. So that again is what we learned last time. L is not, L and omega are not parallel. Okay. On the other hand, if it's a sufficiently symmetric body that these off diagonals vanish, then it will be parallel. So we can see all that right here pretty nicely. Okay, so I decided to add a couple of pages of linear algebra to this discussion here and not go straight to the definitions of the different rotating objects. Because, and I'll go ahead and leave that up there, this is a good place to talk about taking a completely general inertial tensor and diagonalizing it, because there's a really good physical interpretation of that. Good. So we have this. I'm going to go ahead and erase this part. So we're going to be working with this expression right here on the one hand, and on the other hand, so here's the question, can we find an axis? The question is how to find an axis of rotation such that L and omega are parallel. Find an axis of rotation such that L and omega are parallel. That's what we're going to do. We just saw in general they're not. So we have on the one hand, I'm just going to rewrite what we have. So we have, and by the way, I just caught an error. Great when you can catch them. This was L sub k. Okay, this was the kth component. We just did the matrix multiplication for it. I was just mislabeled there. So in order to find this axis of rotation, we have L sub k is equal to sum of I sub k and omega n equals 1 to 3. And if L and omega are parallel, we would have L is equal to I omega, where I is no longer a tensor, where I is just a number. Is just a number. Okay, well I'm using the same letter, which may not be so good. Sometimes you could write this one bold or something like that. You could do a number of things. Okay, so right here, this is a 3 by 3 matrix, but if L and omega are parallel, then this is only a number, right? Because these two vectors are parallel, it's just a number. So that's an important point. That's a number. And we're just going to equate those two ideas. Now we equate the two equations. Equate the two equations. Formulate that somewhere else. We'll write that later. Now write I omega 1, that would be my L sub 1 here, is equal to what I have right there. I 1, 1, omega 1 plus I 1, 2. I 1, 3, omega 3, right? So I omega 1, that's L sub 1 on the one hand in this form and on the other hand in that form. So I'm just trying to set up an equation with this one on the left side and this one on the right side. And now I have I omega 2 is equal to I 2, 1 omega 1 plus I 2, 2. I 2, 3 omega 3. And finally for the last one, I omega 3, I 3, 1 omega 1 omega 2, I 3, 3 omega 3. Hope we can read that. Okay. So we have this, and I'm going to do, maybe I'm going to do two steps in one right here. Because this is just a system of linear equations, and I can write them in matrix form in the following way. Okay, so this one's important. So I can bring this, each of these over to the left side and set it equal to 0, and I'm going to get a matrix, and I'm going to multiply it by the vector omega 1, omega 2, omega 3, and that's going to equal 0. Okay. So we'll do the first row. It's the first row times the column, so it's I 1, 1 minus I on the diagonal, and then I 1, 2, I 1, 3, I 2, 1, and then I 2, 2 minus I 2, 3. I have to make this I 3, 1, I 2, I 3, 3 minus I. So you know I'm going to put little brackets around the diagonal elements. Okay, what kind of a visual is that? So that's matrix times vector equals 0. Well, this looks just like the standard eigenvalue problem. Maybe a less than beautiful choice of letters, too many I's in there, but other than that, yeah, I'm gonna make some room here. So coming down here. This is an eigenvalue problem. Okay. So what we're looking at is the problem of diagonalizing a 3 by 3 matrix. Okay. Eigenvalue problem, comma, to diagonalize the 3 by 3 matrix I sub ij. The only thing we don't like is the letters here right now. So go ahead and let what I'm calling I up here be equal to lambda, okay? then I would be looking at the matrix I minus lambda times the unit matrix times omega equals 0. You know, I'll just put the little subscripts here just to not be irritated by that. And that's your standard eigenvector problem. So the eigenvalues, if you go ahead and diagonalize it, the eigenvalues will give you your principal moments of inertia, and the eigenvectors will give you the principal axes that go along with those eigenvalues, with those principal moments. So, etc. So we're diagonalizing 3 by 3 matrix, and the result is, let's erase this. The result is we now have I sub 1, 0, 0, 0, I sub 2, 0, 0, 0, I sub 3. Those are the principal moments of inertia. So the inertial tensor has been diagonalized. Like I said, the eigenvectors or the subspaces will be the inertia. The eigenvectors will be the corresponding axes of rotation. And the nice thing is, this is always possible based on the type of tensor this is, namely a symmetric tensor. And so you can always do this, and as physicists, we're just going to say, yeah, we can always do it, so we're always going to start out with a rigid body that has a inertial tensor of this form. It's diagonal, because that's always possible. And that means the most general rigid body can be represented like this. It doesn't matter how complicated it looks like. If you located its center of mass and did the diagonalization, you'd have to, you'd locate the principal axes, and those would be the corresponding eigenvalues. So we then have principal axes. So those are eigenvectors. Or we could say eigenspaces, eigenvectors, eigenspaces. It just gives the direction. And principal moments, which are the corresponding eigenvalues. Eigenvalues. And by the way, this is as nice of a physical derivation of an eigenvalue problem as you'll find. Okay? You're trying to find the direction in which L and omega are parallel. So yeah, this is just good for your linear algebra education, to see a real concrete case where you run into your eigenvalue eigenvector problem. And good. So that's what I decided to add to my notes. Good point to have. So now we can talk about the inertial tensor and get some definitions here, and we're going to come to the point where we're always using a diagonal one. Yeah, so make this a nice section of your notes, because it's a good linear algebra application. As good as any. Only thing not so good is the choice of letters here. Too many I's. Okay, so now we're back to talking about the inertial tensor. We want to calculate some of these. The role of symmetry is pretty clear. So let's see here. Inertial tensor. And you know, we can write it sum or integral, doesn't matter. See if we want to write that down. I don't want to write the whole thing out, but I thought I would just put that definition. Okay, the 3 by 3 matrix I'm not going to write out. So let's just do the r squared delta ij minus xi xj. We'd already seen what happens. The diagonals look completely normal to us. Okay, so we have that. So it's diagonalizable. And therefore it can always be written like I have up there, 0, 0, 0, I3. So now we have a number of different cases and definitions. And that has to do with the relative values of these. So if we have I1 equal to I2 equal to I3, we have the symmetric body, it's called the symmetric top, as in a rotating top, right? And any body where these three are equal is then equivalent to, say, a perfect sphere where they're clearly equal, okay? So that's the symmetric top. Then we have, without loss of generality, say I1 is equal to I2, but I2 is not equal to I3. Actually, that's not the symmetric top, that is the spherical top. I mentioned sphere right there. And the point was that it's equivalent to a sphere. If these three are equal. This is the one that's the symmetric top. And then the third possible case, right, this is this, you know, up to permutations. The third possible case, I1 is not equal to I2, I2 is not equal to I3. So they're all different, and that's the unsymmetric top. And we'll see the dynamics here are very easy. Here they're interesting but doable. And here they're really rich and interesting but very difficult to deal with. And then, so we've got those definitions, spherical, symmetric, and the unsymmetric top. And now I'm going to have to make use of this. So these are just properties 2, 3, definition. So here's a property. If you take I1 plus I2, and you're looking at this right here, you're going to have the sum of m, right? Integral dm, or just sum of m. And I1 is 1, 1. So 1, 1 squared, 1 squared plus 2 squared plus 3 squared minus 1 squared. So it's I, so it's x2 squared plus x3 squared, and x2 is plus x1 squared plus x3 squared. Okay. The one that's missing is always the one whose index it is. Okay, so that's going to be greater than or equal to the sum over m of x1 squared plus x2 squared which is by definition I sub 3. And since these are just, up to permutations, what you have is that the sum of two moments of inertia is always greater than or equal to the third one. The sum of two is always greater than or equal to the third one. And now you get an interesting property here. So this was 4, so this is 5. If x3 identically equal to 0, in other words, if we have a planar body, so it's restricted to the x1, x2 plane, a planar body, then what do we have? We actually have equality. I1 plus I2 is equal to I3, because then the x3s here vanish, right? x3s are gone because it's a planar body, so it's just x1 and x2. So this is kind of nifty because you can get moments of inertia for planar bodies really nicely. Okay. So this is an important problem or an important property. See how we're doing time-wise here. Oh, great, we've got nothing but time. So yeah, we have these properties, and we want to work through some dynamics, but first we have to do a little bit of integration. So we won't get to the dynamics today, but we'll do some moments of inertia. And what I'll do is I'll assign them as a homework problem. This has a name here in my notes. This is called the perpendicular axis theorem. I'll write it down here. Perpendicular axis theorem. It's for a planar body. Okay, so now we want to integrate a good example, inertial tensor of the uniform cube. And I'll just get us started on this. Cube of side A. Okay. I'm supposed to draw this. x1, x2, x3. So we'll continue those axes like this, and then a over 2 good luck. Okay. You guys do a better one. But yeah, we're plus and minus a over 2 in every direction. And inertial tensors up there. So first, we see that off diagonals definitely vanish. Just by the symmetry of it, say you had x1, x2, right, off diagonals, delta ij is equal to 0. Okay, so let's go ahead and do this again. We've done this before, but that's fine. So for the off diagonals, I is not equal to j. I sub ij is equal to integral, get a minus sign out front, dm xi xj. We want to do I sub 1, 2 minus dm x1, x2. You've got minus dx1, dx2, dx3, x1, x2. So the point being, let's see here, we've got dx3, then we've got dx1, x1, dx2 x2. And all of these are from minus a over 2 to a over 2. So if you needed convincing on this is just another time to look at it. Both of these integrals here are going to vanish, right? x1 squared over 2, x2 squared over 2. Okay, they're linear going through the origin. Symmetric, linear going through the origin. So yeah, these integrals vanish, and the whole thing's equal to 0, okay? So not for the last time, the off diagonals vanish explicitly. Now, by symmetry, if we can do one of these, we're golden. So let's look at I11. Okay, so now that's our dm, and we have x1 squared plus x2 squared plus x3 squared minus x1 squared. So it's x2 squared plus x3 squared. And we've got the dx1 from minus a over 2 to a over 2. All the bounds are the same there. Then we've got a, oh, you know, I forgot to do the density, but I've got room here. Here's a minus, so I was doing the density, so that's just m over a cubed, and we're done, okay? M over a cubed, these were gonna vanish anyway. This time we actually gotta write that out, so we've got equals m over a cubed, and dx1, dx2, dx3. So the dx1 has nothing to integrate over except for 1. Then we have dx2, x2 squared, minus a over 2 to a over 2. And then we have dx3, x3 squared. So let's see if we can just knock this out. We've got m over a cubed. This one, of course, is just going to be a, right? Minus a over 2 and plus a over 2. This one here is going to be a 1/3 times x2 cubed, evaluated from a over 2 to minus a over 2. So that's 1/3 a over 2 cubed times 2 for the upper and lower boundary. And then the same thing happens again, so that's times 2. So what do we have? I am missing a power of cubed missing a power of a, let's see what's going on here. 2 squared. Oh, I'm not just doing times 2 here, because I'm multiplying by a power here. Times 2, okay, let's get this. There's got to be a mistake right here. Oh, it's plus. It's not, okay, it's plus. So actually the factor of 2 was right, but then plus x3. Okay, nope, back up, we got this. real time, no edit. Let's see what we did here. Real time, no edit. Okay, density dx1 taken care of. So then density dx1. So now we've got dx2. I got this. dx2 x2 squared plus x3 squared. Okay, I'm confusing myself. Let's do this. Let's do this. dx2, dx3, and then x2 squared plus x3 squared. Okay, so that's true. My power, okay, so I knew that was wrong. Once more with feeling. So we've got the m over a cubed, and we've got the dx1 once and for all. So that's just times a. dx2 minus a over 2, a over 2. Now if we do this one, for minus a over 2, a over 2, we're going to have a times x2 squared, because we're only integrating over x3, so a times x2 squared. For the x3, we're going to have plus 1/3 x3 1/3 times 2 a over 2 cubed, because here we're actually doing the integral x3, so we've got the 1/3 a over 2 cubed, top and bottom integral 2 right there. So when we do this integral, we're going to get another a right there, m over a cubed times a. This one here, we're going to have a times 1/3 x2 cubed, so times 2 a over 2 cubed. And this we're going to have 2/3, one more a here, and a over 2 cubed. So let's hope this comes out. We have m over a cubed, and our powers here, we have a squared times a to the 3rd, which is a to the 5th, a squared times a to the 5th. So we've got a to the 5th, and it's just a question of 2/3 times 1/8 plus 2/3 times 1/8 equals m a squared over 4 over 24, which is 6. Okay, that's what's supposed to happen. ma squared over 6. Now let me check the time. Yeah, you see, you gotta be careful monkeying around with these things because, yeah, it's all here now. Okay, so there's our inertial tensor for the cube at long last. Okay, I'll send this up and I'll formulate your homework problem. So the cube is a spherical top, even though it's not a sphere. It's dynamically, we're going to see, it's dynamically equivalent to a rotating sphere. So the next thing we want to do is to get the most general rigid body, and that'll be one in which we have, we're gone here. So I sub cube of side A is equal to MA squared over 6, MA squared over 6, 0, 0, 0, MA squared over 6. Okay, so we have that. Now, to get the most general inertial tensor with I sub 1 not equal to I sub 2 not equal to I sub 3, we just have to get a box. So homework, calculate the inertial tensor. I'll just write I sub ij for a uniform box of sides A, B, and C. And we'll set it up exactly the same way we did this one. So it should only take one of those integrals and then some clever relabeling, okay, to figure out what the whole thing is. And, you know, if you want to draw this x1, x2, x3, you have to cleverly show all three dimensions being different, right? It's a box. You know, probably better to draw the box first and then some axes. So there's the box, and you want your axes to come right out the center. Okay. X1, X2, or X2, X3, like that. Yeah, box sides A, B, and C. So you're going to have your integral dm, of course, will be 1 over, or m over a, b, c this time, right? I had m over a cubed, m over a, b, c, and then you'll have your dx1, dx2, dx3, etc. So it's the same as the calculation I did, but this will now be the fully general example of a rigid body, and I'll just put here as a note, your expression for A equals B equals C has to result in the cube again. So you'll know you have it right because it'll naturally turn back into this. Okay. So that's a good homework, and the interesting thing about that, you need a hardcover book, but a perfect example of such a dynamical, this is soft cover, but I don't have a hardcover with me now. Such a top, such an unsymmetric top is an example is just a book. Books of various thicknesses, they have 3 different dimensions and they're reasonably uniform. So if you take a good, well, I don't want it to be too good of a book, but you take a hardcover book and you wrap a string around it, tie it shut so it can't flap around, you can see some interesting dynamics. I'll bring that to class next time, or the time after. So you get some, this is, of course, much too flexible. It's what I have here on hand. So that's where we're going to leave it. Just construct this guy, this uniform box inertial tensor. It'll reduce to this one in the limit A equals B equals C. Integrals are just the way we did them. And we'll start talking about dynamics sooner or later. Actually, of course, we're out of time right now. What we want to also do, and that'll take a little more work, we want to get the spherical, not the spherical, we want to get the inertial tensor for the ellipsoid with 3 different axes. That's a worthy project because our rotating heavenly bodies are ellipsoids. Okay, they're generally not perfect spheres, and that plays a big role. Okay, enough for today. We'll leave it at that. See you guys next time.